The sun never stopped sending the particles scientists were looking for. For more than 30 years, the evidence reached Earth exactly as nature intended. Yet deep beneath a mountain in South Dakota, scientists kept finding only a fraction of what every calculation said should be there. Either the sun had failed in a way no one could explain. One of the most careful experiments ever built was quietly making the same mistake year after year, or something invisible was changing before anyone realized it. The answer would overturn one of the basic assumptions of particle physics, not because new evidence appeared, but because the old evidence had been arriving in disguise all along. Nearly a mile underground, inside the Homestake gold mine, a steel tank held about 100,000 gallons of ordinary dry cleaning fluid. Raymond Davis Jr. had placed it there for a simple reason. Cosmic rays constantly bombard Earth's surface, producing signals that could overwhelm the traces he wanted to measure. Beneath thousands of feet of rock, much of that noise disappeared, leaving only the faint possibility of particles arriving from the sun itself. The detector did not look traumatic. Week after week, solar neutrinos streamed through the mountain, through the steel walls, through the liquid inside, and almost every one of them continued on without leaving a sign. Only on rare occasions would an electron neutrino strike a chlorine atom and transform it into a radioactive argon atom. Every few months, Davis bubbled helium through the enormous tank, collecting those atoms one by one. Sometimes there were only a few dozen to find. The measurement depended on counting individual atoms recovered from an ocean of liquid. Then the numbers settled into a pattern. Instead of matching the predicted signal, the detector measured only about 1/3 of the expected electron neutrinos. There was no sudden failure, no drifting instrument, no obvious contamination. The particles that should have appeared kept failing to show up. On the graph, the measured line stayed far below the theoretical one. Attention turned toward the sun itself. John Bacall had spent years calculating the nuclear reactions inside the solar core. His standard solar model predicted how many neutrinos should emerge from the fusion processes powering the sun. Some critics wondered whether those calculations were wrong. A relatively small change in the sun's core temperature could explain why so few neutrinos seemed to arrive on Earth. It sounded more reasonable to question an invisible furnace 150 million kilometers away than to rewrite the foundations of particle physics. But the chart would not move. Predictions became more refined. Measurements became more precise. Across decades of checking, the gap survived. Each improvement should have exposed a mistake somewhere. Instead, the same contradiction came back cleaner than before. The evidence had not disappeared, it had become harder to explain. Inside mountains in Japan, another kind of detector began watching the same sun. Huge tanks of ultra-pure water waited for brief flashes of blue Cherenkov light. When a neutrino scattered an electron inside the water, thousands of sensitive detectors could record the signal almost immediately. These instruments were not using chlorine. They were not extracting radioactive atoms months later. They were observing neutrino interactions through an entirely different physical process. Still, the sun looked incomplete. Kamiokande, followed by the much larger Super-Kamiokande detector, confirmed that neutrinos were arriving from the direction of the sun, yet the count remained too low. The same missing fraction appeared in a different experiment, with different materials, on another continent. Whatever had happened inside the Homestake tank could no longer explain the discrepancy by itself. One possible explanation after another fell away. The detector chemistry was no longer the obvious suspect. The measurements agreed across independent instruments. Helioseismology, the study of sound waves traveling through the sun, also confirmed that Bacall's model of the solar interior accurately described its temperature and density. The sun was behaving as expected. The shortage had nowhere left to hide except inside the particles everyone thought they already understood. In Canada, another underground laboratory prepared an experiment unlike any before it. The Sudbury Neutrino Observatory filled a transparent acrylic vessel with 1,000 metric tons of heavy water, surrounded by thousands of light sensors. This detector could do something no previous experiment had managed. One reaction responded only to electron neutrinos. Another responded to every neutrino flavor equally. For the first time, scientists could count not only the particles that still looked familiar, but the full population passing through the detector. The result split the mystery in two. One measurement looked like every disappointing result that had come before. Electron neutrinos still accounted for only about 1/3 of the predicted total. The other measurement changed the meaning of the entire gap. When all neutrino flavors were counted together, the total matched Bacall's solar prediction almost perfectly. The missing particles had never disappeared. They had arrived with different identities. The contradiction dissolved without changing a single measurement. The Homestake detector had never been built to recognize muon or tau neutrinos. It could only respond to electron neutrinos. During the journey from the Sun to Earth, some of those particles had transformed into other flavors through a process now known as neutrino oscillation. The detector had faithfully reported what it was capable of seeing. Nature had simply been doing something the existing standard model did not allow. And that carried another consequence. For neutrinos to oscillate between identities, they could not be completely massless. One long-standing assumption inside particle physics had to be revised. The decades of disagreement between theory and observation had not exposed a failing sun or a flawed detector. They had exposed an incomplete description of matter itself. The solar neutrino flux chart remained the same physical object. Its lower line never moved. The upper prediction never needed to retreat. What changed was the empty space between them. By the end of the investigation, that gap no longer represented missing particles. It recorded the portion that had changed identity before reaching Earth, while tens of billions of solar neutrinos continued to pass through every square centimeter of our bodies each second, almost all of them unnoticed.